Welcome, everyone. Looks like we are at the top of the hour, 1 o'clock Eastern, noon Central. Thank you so much for joining me today and my colleagues for detailing air barriers. My name is Isaac Sorensen. I'm the National Architectural Sales Manager with W.R. Meadows based in the Northeastern U.S., New York City. Thank you so much again for your time. I really appreciate you joining us today for detailing air barriers. Our presenter today is Mr. Scott Wolf. Scott is our Midwestern Dedicated Architectural Services rep in the Midwest, based in the Chicago area. Before I pass the presentation over to Scott, though, I want to go over a few things with you. Everyone will be muted for the duration of the presentation, and if you have questions, please type your questions into the Q&A box and double check that you're addressing your questions to all panelists. We will be monitoring the Q&A and we'll be attempting to answer your questions in real time. However, if your questions require a lengthier explanation or a bit more complex, we may hold on to them until the end of the presentation, and we will definitely have some time at the end of the presentation to answer your questions verbally. And in some cases, we may need to get in touch with you for a longer explanation via email. This is an AIA accredited presentation. Everyone will be receiving certificates sent to the email addresses you provided at registration. If you included your AIA number, we'll also be submitting these credits directly to the AIA. And lastly, on the screen, you'll see some email addresses throughout this presentation. info@WRMeadows is our general. If you're looking for a copy of the presentation or would like to get in touch with your rep or have an additional question for us in the future, please shoot us an email at info@wrmeadows.com. And of course, specific questions to the presentation can go directly to swolf@wrmeadows.com. And at this point, without further ado, I want to turn over the presentation to Scott.
Isaac, thanks. Yeah, appreciate it. Thanks a lot, Isaac. Appreciate the intro. As Isaac mentioned, any questions that we're not able to get to, please feel free to email me directly at the email on the screen, or feel free to call my mobile phone, which is listed right here. So, but we will have some time afterwards, as long as anybody's willing to field some questions. So with that, we're going to go ahead and jump in. Got a lot of stuff to cover. Just a little bit of housekeeping here. W.R. Meadows is a 96-year-old company. We're on the doorstep of celebrating our centennial here, coming up 4 more years. We do market globally with about 13 facilities in North America. Most of those are manufacturing and distribution hubs. So for any projects outside North America, please let us know. Be happy to work with you. This is just a snapshot of the Meadows family of products, Division 7, Division 3 products, which we'll show you again at the conclusion here. So with that, let's go ahead and jump in. Got a ton of stuff to cover here, and I'll get started. So learning objectives today are going to just be to examine critical air barrier connection points and try to understand the importance of getting them right the first time. Also try to identify the difficult to detail conditions and understand how to best address them with the arsenal available transition membranes and accessories that manufacturers provide. We'll also look at those transitional areas that are very key and critical to getting air barrier connections right, and basically, stopping the bulk air transmission and or water transmission, which is really the goal of really, aside from the points made in this PowerPoint, stopping bulk air leakage into and out of the building envelope is really what's most important. We'll also look at some of the peripheral material interfaces, wall to foundation, wall to roof connections. These are also very, very important and really best identified early on in the design process. I always like to suggest latent schematics is a good starting point. So the goal, sort of to be kitschy about it, the goal of this PowerPoint is to avoid the complicated building syndrome. These images really capture, really in essence, what we're trying to convey here. Just understanding that the more complex the geometry of a structure, the more challenging, frankly, it is for connecting the air barrier to these obtuse angles, if you will. Great article referenced here in one of many illustrates this problem that we have. We're certainly not trying to eliminate creative license to create really cool looking structures, but just an understanding that the more difficult or challenging the structure is, the more challenging it will be for the installers, and so we'll move in. So building enclosure elements, really, this is what we start with. So what is the building enclosure? The building enclosure, of course, is a conglomeration of the 4 control layers: air, water, water vapor, and thermal. Thermal, of course, being our insulation. With that, the extension of the 4 control layers, of course, are the fenestration, the doors, the windows. These are operable building envelopes that contain the 4 control layers just mentioned. The structural backup wall, roofs, foundations, floors, these are what all of these systems are subsequently applied to. Certainly can't lose sight of that. But the point I always like to make in this slide here is that the air barrier is and should always be considered the last line of defense against air, water, and where appropriate, water vapor control. What that means is basically the air barrier, and I always like to call it an air barrier, should be applied to the structural elements that we just listed here. In this graphic in the upper right-hand corner, the air barrier is applied to the structural backup wall behind the exterior continuous insulation, because I suspect that I'm preaching the choir that everybody knows that the code largely now advocates for a layer of exterior continuous insulation. There might be one manufacturer that cites that a layer of extruded polystyrene rigid insulation is an acceptable substrate to apply an air barrier to. I would be vehemently opposed to this. This type of material is not a structural material like CMU, cold form metal framing, and gyp sheathing, plywood, for example. The one exception to this would be if a framed wall were to have an insulated sheathing, which is the language used by the manufacturers of these types of products, where we have a layer of rigid insulation bonded to, say, like an OSB panel, and the OSB panel, of course, is a structural material to which the cladding will be applied. In that instance, certainly, yes, we would typically see an air barrier likely applied to that exterior face of that insulated sheathing, but that's I would say the majority of the times we want to see the air barrier applied behind the continuous, like we see in the upper right-hand corner. To zoom in on the fenestration here on the left, another important point to be made about the building enclosure is to keep in mind that the IGU, the insulated glazing unit, as mentioned, is basically a continuation of the 4 control layers. If that IGU is offset in any way to the primary thermal layer that's on all 4 sides of the window, that creates an offset condition, and that inevitably can create a thermal bridge, more important in heat-dominated climates. And obviously thermal bridges equate to condensation. Condensation equates to moisture and potential mold development and potential degradation of moisture-sensitive materials. Gypsum sheathing and gypsum wall panels are susceptible to a constant long-term moisture exposure. Any cellulose-based materials, wood framing, craft facing on bad insulation, for example, all can be compromised. Even steel components obviously can rust, and we'll see examples of that moving in. Air barrier assembly, I believe this is probably very remedial, but an air barrier assembly is just simply a collection of multiple materials: primers, termination sealants, through-wall flashings, transition membranes, and the primary air barrier, whether it happens to be a sheet, liquid, or board type, working in concert, obviously, to stop the transmission of air, water, and or water vapor. Air barrier components are quite numerous. These are the accessories. The primary air barrier, of course, self-adhering sheet, mechanically fastened, liquid applied. Transition membranes are certainly used in more often in fluid applied applications to wrap outside corners to ensure that we have the continuity of the air barrier at the apex of these corners. Primers, adhesives, these are used for, self-adhering transition membranes, self-adhering air barriers. There are a lot of pretty remarkable primerless types of products out there that obviate the need for a primer. But in some instances, their primer may be needed. It's rare that we ever see a project site that's dust-free and dirt-free, so hence the need for a primer to bind with any loose residual dust that might act as a bond break. Liquid flashings are not anything new to the industry, but they're a great alternate to these self-adhering membranes because they eliminate the need for primer. They really create a two-step process with what is a four-step process with the self-adhering membranes. And termination sealants. Termination sealants are an integral component to an air barrier, and these are used typically to seal cut edges of transition membranes through wall flashings, and also in the accidental application of a self-adhering sheet air barrier if we have a reverse lap condition. And it's not the end of the world. I always like to state very emphatically that if an installer unfortunately installs a self-adhering sheet air barrier in the reverse condition, they were to say start from the top and work their way down and have that exposed reverse lap, it doesn't need to be turned off. All they need to do is hit that leading edge with termination sealant, knock the edge down with a drywall knife to allow the water to shed. Manufacturers generally accept that as acceptable. Air barrier types are quite innumerable, almost innumerable. Self-adhering sheets, fluid applied air barriers, mechanically fastened sheets, which we've of course seen used in industry for at least half a century at this point. Rigid insulation and foamed in place insulation are also qualified. All of these are qualified by the International Energy Conservation Code, or IECC, as being an air barrier. Rigid insulations and foamed in place insulations are great products. However, I generally tend to take exception to them, with no disrespect to the manufacturers of them, marketed as an air barrier, in essence, all four control layers. Reason being is that these rigid insulation types, while they meet the IECC definition of what an air barrier is, they're very stiff. So they have very little elongation and tensile properties. So if we consider, say, a mid-rise, high-rise structure composed of steel framing that's subjected to a lot of racking forces, X, Y, and possible Z-axis movement, the taller a structure goes, the more subject it is to wind forces. If this is all four control layers, air, water vapor, and thermal, and the 4x8 sheet of this becomes compromised and cracks, we've now compromised all four control layers. Hence the reason why many of us have been specifying quote, elastomeric air barrier behind this insulation. So if this became compromised, we still have a plane of air tightness behind it. I will make a strong promotion for foamed in place insulation, or AKA spray foam. Spray foam is also a phenomenal product. It eliminates the need for taping the ends and edges of the application. But more importantly, spray foam insulation is generally fully compatible with virtually all types of air barriers applied today. Now that is probably the most robust and probably, in my opinion, the best wall to have an air barrier applied, spray foam applied to an air barrier, excuse me. Foam conforms to irregular shapes, and the only exception of its compatibility I would question would be silicone type air barriers and self-adhering vapor permeable sheet air barriers. So I would check with the manufacturers on that, but virtually every other type, the acrylics, the STPEs, the self-adhering modified bituminous sheet air barriers are generally very compatible with this, irrespective of manufacturer. And so as I mentioned, the IECC does acknowledge quite a number of different air barrier materials, plywood, OSB, the aforementioned rigid board stock insulation types, cement board, exterior gypsum panels, gypsum sheathing are all qualified as being an air barrier. Cast in place concrete is an air barrier, even precast concrete. I generally tend to not suggest an air barrier for a precast concrete panel because for several reasons. One is that the concrete is in many cases created in a controlled environment. It's properly consolidated. The matrix is very, very tight, and made even more efficiently so if that precast concrete panel is a composite of both an exterior and interior concrete skin, so to speak, with a sandwich of rigid insulation in between, to obviously improve its thermal resistance. So in that instance, I would say save money on the project, but do address all of the penetrations, the wall to foundation, the wall to roof connections, rough openings with an air barrier flashing. That would be my suggestion. Panel to panel connections, of course, too. But as we see here, all of these materials qualify by the IECC based on the ASTM standard noted there at the bottom as far as the air permeance or air leakage. In the design specification, just concentrate on a couple of points here. The second bullet point is probably the most important, in my opinion, is to ensure that each listed manufacturer is able to provide all of those requisite accessories, the primary barrier, the through-wall flashing, termination sealants, primers. Thankfully, most manufacturers are able to provide this. However, there are a small number out there that do defer to another manufacturer for their sealants, possibly for another manufacturer for their primers. So it's much better when everything is allocated from one manufacturer. Thus eliminates the whole compatibility question, because as us manufacturers, we are fairly regularly asked to write letters of compliance or compatibility with our air barrier and someone else's through-wall flashing, for example. We see that a lot. So ideally, try to specify all from one manufacturer. And a lot of these little maladies can be rooted out in a pre-construction meeting. This is something that is probably part and parcel with everybody on the call here today. When writing a fluid applied air barrier specification, I generally like to suggest to keep the chemistries in the same family, so to speak. So in our world today, for liquid applied air barriers, there are really three main categories: water-based acrylics, STPEs, which is an acronym for silyl terminated polyether. The STPE chemistry is a very interesting technology that is not really new. They've been around for probably at least 15, 16 years at this point. But STPs are sort of a hybrid of polyurethane and silicone technologies with some other polymers, of course. And what makes those very attractive is their compatibility with virtually anything that comes into contact with them. And excuse me, the silicone type air barriers. Ideally, if it's possible to just keep all water-based acrylics, all STPEs, or all silicones, that would be the preferred. And the last point to be made here is that also when specifying fluid applied membranes, we try to implore to keep them of like thickness. I'd like to always refer to AI Master Spec, their spec section 072726 for this particular subject. Master Specs offers three different build thicknesses: high build, medium build, and low build. A high build fluid applied air barrier is specified as a membrane that is not less than 35 mils dry film thickness. The medium builds will generally be between 30 and 15 mils dry film thickness, and the low build is between 6 and 15 dry mils. Why that's important is that, well, the point to be made here is that all of these different build thicknesses meet the industry requirements for air permeance, water vapor permeance, fire resistance, NFPA 285, air barrier assembly, air leakage, E2357. But this is where the similarities tend to end. The thinner a membrane is applied or manufactured, pretty much most all of the thin film low build types in their technical literature are specified as a plural application. And the reason for that is when we apply a thinner membrane onto a porous substrate, and of course we're showing the most aggressive example of this, CMU or block under magnification, is that the substrate wants to pull a lot of that moisture out of the membrane, making it more, frankly, unwieldy to ensure that we're going to get that correct dry film thickness. The problem is if we apply it just at a single lift application, there may be some areas of discontinuity in the application. The higher or the thicker we go with the membrane, like a high build, which is specified commonly, it's say between 70 and 90 mils wet film, and with maybe 60-70% solids, will dry back to anywhere from say 35 to 45 or 50 mils dry. There's so much more body and more material there that we generally, in many cases, don't have to apply a plural application. But the thin films generally tend to be, for all intents and purposes, a plural application. So my humble suggestion is I always like to prefer the high build for critical use structures like hospitals, museums, libraries, data centers. Not to say that the thin films aren't applied in those types of applications. However, a quick other side note to the thin film is that EIFS manufacturers also typically make their own air barriers, and they often tend to reside in the thin or low build application. There is also another conundrum that comes with that is EIFS manufacturers, where a warranty is required for an air barrier, EIFS manufacturers will not warrant their cladding unless their air barrier is applied behind it. So that becomes almost a sole source type of thing, but that's fodder for another discussion at another time where we can talk about that offline. But that's something that specifiers certainly, if they aren't already aware of it, should be at least aware of. Material compositions, considerations, I just recently added this, but excuse me, but I think it's something that's important to understand. Water-based acrylics are probably still holding sway as far as the majority of air barriers specified and used. But there is a small category in the water-based fluid applied air barriers that are of an asphalt-based composition. These asphaltic fluid applied air barriers can carry a 25 to 30% cheaper price tag. However, these types of products have a maximum exposure before they're covered with the cladding of typically not much more than 6 weeks. This is really important to know. The water-based acrylics, the STPEs, the silicones can be exposed perhaps indefinitely, but the acrylics and the STPEs can feature 6 to 7, 8, 9 months exposure before the cladding gets installed. It's always advised by manufacturers to apply the cladding as soon as reasonably practical after the application. But these acrylics, as we see in this image here, give them enough time, after a couple of months, they will start to alligator. And they're also severely restricted in NFPA 285 compliant assemblies. The only NFPA 285 assemblies that they're really applicable are block, backup wall, mineral wool insulation, and a masonry type of cladding. So if you can kind of see the connection here is that the entire wall has to be basically 100% non-combustible as we define it. So in specifications, this is just a quick reference of the standards that we'd like to see specified. E2178 is the individual air leakage, E2357, the air barrier assembly standard. The maximum air permeance listed to meet this requirement, and should really frankly be what the specifications should be written on. Anything lower than either of these 0.004 CFM or 4/100ths of a cubic foot per the E2357 standard doesn't mean the product's any better, just means that the product's long exceeded. So these should be the demarcation lines to meet these standards. And D1970, the self-sealability standard, I think has been abused as far as people relying on it perhaps a little too much. It certainly does raise the bar of performance for a fastener penetration through the membrane, but it's important to acknowledge that the fastener heads have to be pulled down tight to the membrane for this to work in reality. So larger fastener penetrations like carriage bolts or cap screws for that matter must be sealed with supplemental termination sealant. And this standard here, coming from the gypsum world, I'm particular to anything gypsum related, but ASTM C1280, the standard specification for application of exterior gypsum panel products freezes sheathing, is a really important standard, certainly referenced in the gypsum sheathing spec section, but It when installed correctly, we don't want to leave, again, the air barrier installer held in the lurch to have to repair some poorly installed JIP sheathing applications like we see in the upper right-hand corner. The standard does state that we don't want to overdrive the fasteners. If we overdrive a fastener in a glass mat JIP sheathing and break the glass mat facer, the panel at that point attached to the framing is frankly rendered not attached at that point. So we've now got a compromise in our sheathing application. Plus, also the ends and edges must be held in reasonable contact with each other and not gapped and poorly aligned like we see here. So again, the easier we can install the air barrier, the better the quality, the deliverable. Boy, it's hard to say. So, but it's very, very important. So I would always suggest including C1280 at least somewhere in the construction documents. So really, what is a code correct air barrier? Chapter 14 of the code, or the IBC, literally initially states type 1 felt or other approved materials, but it does frankly defer to these other code standards of the IECC, for example, for a quote continuous air barrier throughout the building thermal envelope. And LEED version 4 also defers to ASHRAE 90.1. All of these lead back to the IECC ultimately for continuous air barrier requirements. Or we could certainly build them to the absolute minimum, which is 15-pound building paper. And yes, this is a project not too far from where I live, so I was just kind of surprised to see that. This is just a really important slide that perhaps might not really be so much in the application detailing of air barriers, but it is important to at least acknowledge the water vapor permeance of all the materials within an assembly, and acknowledging the fact that in our world today, the requirement for the use of exterior continuous insulation is really important. When we use closed cell rigid insulation, the pink and the blue XPS type of insulation, extruded polystyrene, generally when we get to 1.5 inches, frankly probably 1.25 inches, or greater, but typically 1.5 inches, this material becomes vapor retarding, i.e. becomes a quote vapor barrier. What's important about this is if we specify rigid insulation that really in essence becomes a quote vapor barrier, that everything from that point inward must be frankly vapor diffuse open. So the point to be made is that if we have exterior continuous insulation with a perm rating less than 1.0 perms, that we should eliminate the interior poly vapor barrier that's normally specified, or in many cases specified, behind the interior drywall. If we do have a vapor restrictive poly behind the interior drywall, or we have vinyl covered wallpaper, oil-based paint, epoxy type paints, we've now created a double vapor barrier condition. Reason I bring this up is that the 2015 code and its subsequent iteration in the 2021 code basically states that when the rigid insulation has a perm rating less than 1, everything from that point inward must be vapor diffuse open. The passage is I think a little convoluted, but that's in essence what this passage is in essence stating. We want to avoid the double vapor barrier condition when the rigid insulation is basically acting as a vapor retarder. So coordinate with the interior design team for these types of conditions to make sure that the interior finishes are also vapor non-restrictive, I guess. So we'll move on, but check out our air barrier PowerPoint on permeable versus non-permeable. So, but the IBC does define latex paint as being above 1.0 perms. The IBC also defines as vapor permeable membranes as typically those having a perm rating of 5 and higher. So during the plan review, and naturally not surprisingly, we want to make sure that all of the connecting points of the structure are well, frankly, connected. Wall to foundation, wall to roof connections. Certainly a truss roof promotes a lot of challenges that we deal with on a project by project basis. Sources of bulk air leakage are almost too many to count. But if we do have compromises in our envelope, and we happen to have, say, a bad insulated exterior wall. This is something that can and has been studied by ASHRAE and found that bad insulation can be reduced. The thermal R value of bad insulation can be reduced by upwards of 80% if we introduce air and convective air looping, moisture accumulation. All of this can degrade thermal performance to a significant amount. But if we get the penetrations properly sealed, there is a thought that this might allow reduction of our mechanical sizing requirements. Early in my career, I was told, or alleged to have been told, that mechanical sizing requirements are generally oversized to account for a certain amount of air leakage throughout the building envelope. But as we have better quality control in installation of air barriers, this again might provide an offset and reduction of our mechanical sizing requirements, again providing an offset to the cost of an air barrier. Some might suggest 1 to 1.5% of a project budget could be contributed to the air barrier installation, the material costs and installation. Obviously, the more penetrations, the more window openings, the more expensive the air barrier. But certainly a data center, it could certainly be far lower than that because it's just all tilt up and we have very few windows, for example. But if we do get some introduction of air leakage into our structures, these are just some lovely graphics of what could possibly happen. Compromising to the cladding, moisture traversing laterally, vertically through capillary action is what we see in the center here, and vapor diffusion transfer through porous materials like block and CMU, creating a dissolution of the mortar salts that we see in a good example in the lower left. And again, the greater the temperature delta and the greater the vapor pressure delta between inside and outside environments, this creates an opportunity for air to transfer through any areas of compromise, like we see in the strip mall on the lower left here. So let's get into the meat and potatoes here. Designing for ease of constructability. When designing, detailing an air barrier, do consider again the ease of which the air barrier is installed. A great example of this was Specifier had sent me a batch of pictures, one of which is in the upper right-hand corner, asking what type of air barrier should I use, and I told them, I said, quite honestly, I don't have anything for you. This is going to be almost impossible to detail. If we have a block backup wall with mortar pooching out from the joints, we have whole ends of the block that are frankly giant holes. The block we see at the rough opening, standing proud of the main wall sections. All of these conditions have to be addressed before the air barrier can be installed. It doesn't even look like the block is properly even set level there at the rough opening. So I just told him, I said, tear it out and start over. Unfortunately, the owner of the structures, that was pre-existing, of course, was not too keen to that, and I heard that they ended up leaving a lot of these conditions as is. So thankfully, I did not get any of that work. My competitor did, so I couldn't have been happier for him. But again, the easier the barrier can be installed, the better the quality, the deliverables. So it's really important to have a smooth flush surface, especially when the backup wall is composed of block. Here's another good example. This was a project I was working on roughly about a year ago. It was an adaptive reuse of several courses of white masonry exterior wall. A couple of key important points to point out here is this type of wall. In this project, I suggested that they don't consider any air barrier because masonry is as we know, an air barrier. I did suggest identifying key areas of compromise. If there are any cracks, pre-fill the cracks with a non-sag polyurethane sealant. And specific to this image here, the plan was to just simply remove and replace and reflash the rough openings with new bucks. The problem is that the air barrier transition membranes, per the industry, are specified to be applied typically to 3 inches minimum onto each adjacent plane. Now, the detail on the left is certainly able to accommodate that. We see a 2x4 window buck, which is obviously 3.5 inches. So if the industry requirement to have a minimum 3 inches of transition membrane or window flashing, in this case, to each adjacent plane, we can certainly accommodate that on the horizontal. But transitioning on the vertical, a 2x material, of course, is 1.5 inches. That's really not enough for any self-adhering sheet membrane. It'll certainly be able to be applied, but it's not in keeping with that minimum 3 inches onto, again, each adjacent plane. Then if we traverse laterally across the exterior course of brick, as we see, the brick is commonly going to probably have some holes in it. It's going to have potentially some mortar droppings, going to have dust, dirt, debris, all which is going to act as a bond break. And that's really not a conducive environment. The last step of any self-adhering membrane, of course, is to hit it with a roller. So that vertical 1.5 inches is just not going to be logistically easy to get that membrane to get a foothold. So what I proposed to this particular project architect, I took the drawing, I remarked it up, and suggested introducing a second window buck, a pressure treated and sloped window buck, because we always want to have give the water a place to go, give it a slope to shed the water away from the structure. And that way we now have a very cohesive surface to apply the self-adhering transition membrane onto the sill. And then secondarily to that is I suggested a self-adhering aluminum faced peel and stick flashing for the windowsill. And reason I suggested self-adhering aluminum is that these types of membranes have generally the lowest water vapor permeance of all self-adhering sheet air barriers. And secondarily is that an aluminum facer provides pretty much universal compatibility to any of the silicone or urethane sealants that the window manufacturers require. So we have full compatibility, we have the lowest water vapor permeance, we wrap that up a minimum of 6 inches onto the jamb, and we've really got a nice sill pan application. Typically, I would also recommend liquid flashings for the jamb and the head conditions for the same compatibility question, because these STPE type liquid flashings are highly compatible with virtually anything that any type of sealants that we throw at them. This is not really an air barrier detail question so much as it is a discontinuity of the thermal layer. And we certainly want to point this out, that if we have any breaks in the continuous exterior insulation, it's generally not a good idea, but it's always good to point these out. And then we get to the wall to roof connections. This example here illustrates where the air barrier generally is not likely to interface with the roofing membrane system. And in this example here would be frankly my preferred if we were to have the air barrier not connecting with the roof membrane system. We don't have to be concerned about the compatibility issue. However, if the air barrier does have to interface with the roofing membrane system, it should be applied in a manner that A is fully adhered, and B, the transition membrane that's connecting the air barrier to the single ply roofing membrane system should be fully compatible with that roofing membrane system. Now, I'm stating a single ply roofing membrane system because this is probably far and away 80–90% of the roofs installed today. Rarely do we see modifieds anymore. Not that there's anything wrong with modifieds. I'm a big proponent for them, but single ply roofing membranes, PVC, TPO, and perhaps maybe to a slightly lesser extent, EPDM roofing membrane systems are not compatible with the typical rubberized asphalt self-adhering transition membranes. So there are options to that, where some manufacturers provide a self-adhering butyl transition membrane. Butyl is basically non-asphalt containing. And so secondarily to that is self-adhering butyl transition membranes are not negatively affected by the high solvent containing primer adhesives that are used to secure single ply roofing membranes. So We want to make sure that the manufacturer either has is a self-adhering butyl transition membrane or perhaps a third-party self-adhering transition membrane. There's a manufacturer of a standalone product that is used. I'm not at liberty to say it on an AIA presentation, but there is a product out there that's long been used for decades as a qualified bridging membrane to bridge air barriers to these types of single-ply roofing membrane systems. So again, I'm going to harp on this particular condition, but it's very important that the roofing membrane is applied to the air barrier in a fully adhered manner. This whole image here has an interesting story behind it, and no, I'm not really sure why the sheathing is draping over on top of the brick, but I took it for partially for that reason, but partially because the image shows the single ply roofing membrane is not fully adhered. It's just simply mechanically fastened. And again, I really implore that the single ply should really be fully adhered, ideally in shingle lap fashion on top of the air barrier. If we leave this type of roof membrane mechanically fastened, and even if it is mechanically fastened onto an air barrier, but not fully adhered, and again, the greater the temperature delta and vapor pressure delta between inside and outside, especially in heat-dominated climates, the result of that could possibly result in, this type of condition here. So this is really what we're trying to avoid. But again, we want to make sure that wall-to-roof connection is made via a compatible accessory membrane, and that connection, of course, is fully adhered. So enough of that. Get off my soapbox. So other difficult to detail conditions are shown here. The detail in the upper right-hand corner is it came from an interesting article that came in the Construction Specifier magazine, I want to say sometime 2016, written by Wisjani, titled Boxing Out Air Barriers. And again, it addresses the ease of which an air barrier can be detailed. A steel beam coming out at an obtuse angle from an exterior wall creates a little bit more of a challenge to get these, again, our self-adhering membranes wrapped into a very complex shape. If we can just create a right angle, it's a lot easier to detail a self-adhering membrane at a right angle than it is to form it around the flanges of the steel beam. Pipe penetrations are another example. I'm again a big proponent for referencing the National Roof Contractors Association guidelines in their roofing and waterproofing manual, where they recommend having a minimum 3-inch offset from one pipe to the next. Now, I can almost hear everybody, a lot of people stating that that's not really realistic. And I realize that in many cases, pipes have to be clustered close together. The difficulty with that is that even if we were to flash those two pipes, as we see in the graphic here, together, where the pipes are touching each other, we can't really be 100% sure that that's going to be airtight, watertight, and vapor tight where those two pipes are coming together. One possible workaround that many have proposed is to use a closed cell spray foam. Closed cell spray foam is qualified, as we now know, as an air barrier. Again, but however, it's very, very stiff. So in my opinion, that's going to be a medium to short-term solution to air seal around these pipe penetrations. Possibly where we have a cluster of pipes close together, we might consider applying a chase around it, a box like we see in the upper right-hand corner. That would be another workaround. But we have to at least acknowledge the fact that where we have gypsum, we have EMT, these are two disparate materials that are going to expand and contract due to changes in temperature from one another. And if we just apply a lower tech solution, we may experience some air infiltration at this point here. Metal pan decks, another difficult to detail condition. But this is where liquid flashing can certainly earn its keep, because it's a lot easier to just gun out a viscous material and then just spread it with a drywall knife to the required thickness and to the required adjacent transition onto each dissimilar material. So there certainly are options out there. Other difficult to detail conditions involve a steel beam penetration. If if anyone's not yet quite aware of the Gypsum Association, I've long used their website. It's a great resource. All of the information is free for the downloading. Their GA 253 is a good parallel document to the C1280, but we want to ensure that sheathing to penetrations are installed with the same tolerances as sheathing to sheathing connections. And again, that's a reference from C1280. GA 253, where gypsum sheathing meets projecting surfaces, the gypsum sheathing shall be neatly scribed and cut. So again, what we're advocating here is to a higher level of frankly workmanship, where the gypsum sheathing installation is called for. Make one more reference from the Air Barrier Association of America. And I'm so glad to see this in their specifications, that they also address provide mechanically fastened, non-corrosive sheet metal or other manufacturer-approved transition material to span gaps greater than 1 inch in substrate plane to make a smooth transition from one plane to the other. Now, a lot of air bearing manufacturers have their termination sealants capable of spanning gaps up to 1 inch. They're their moisture cure termination sealants. I think that's okay. I would be more comfortable recommending, say, upwards of no more than a 1/2 inch gap where these types of penetrations are involved. But we have to pre-seal those and then allow them to cure out before we apply the transition membranes. But we want to really, again, advocate for a better practice here. So let's move on. Other difficult to detail conditions. Another example of a project roughly from a year ago. This was, I believe, in the Philadelphia general area. This metal steel shelf angle that we see on the left, it's not the same one on the right, just for information's sake, but the metal shelf angle on the left was installed before the air barrier installer was able to, well, install the air barrier. The difficulty there is that vertical leg of that L metal angle is 8 inches high. So it pretty much made almost an impossible condition to get the air barrier to be continuous down to the rough opening. So they came to us and asked, well, what can we do? And they said, well, it's almost impossible, pretty much is impossible to get a self-adhering through-wall flashing in that condition, or an air barrier or transition membrane. And liquid flashing would be almost as difficult or challenging to get installed there. The easiest solution was something, again, that I don't normally like to suggest, but ultimately it has to be approved by the architect of record, is again the use of a closed cell spray foam. That was the easy out answer for that one. So again, pre-construction meetings are a way to help root out these conditions before they get assembled, before the air barrier installer. Other air infiltration, exfiltration causes exceeding of the building material properties. The upper left-hand corner example was of one of 2 projects I was involved in, gosh, probably about 10, 12 years ago. The air barrier in this case was installed in the middle of June, the hottest, most direct sun, hottest days of the year. The ambient air temperatures for about 3 or 4 days was probably hovering around 100 to 101 degrees Fahrenheit. And that was often enough to basically exceed the air barrier material properties as well as the substrate material properties. This was a local community college, 40-foot high wall, roughly 240 feet long. And it was determined that there were no control joints on the exterior cold form metal framed wall with exterior gyp sheathing. Just for example, 100 foot length of gypsum sheathing, gypsum panels, given a 100-degree temperature delta, can grow and shrink upwards of 1 inch. And if we think about 1 inch, that's often enough to exceed, obviously, both the substrate material physical limitations as well as the air barrier, and it certainly did. Another quick side note to that project, which is also important to know, is to understand that certain materials like the 40 mil self-adhering transition membranes, typically the SBS rubberized asphalt transition membranes, as an industry average, again, irrespective of manufacturer, have about a maximum service temperature of about 158 degrees, again, plus or minus 5 degrees, depending on manufacturer. In this project, the installer used that standard duty transition membrane as a through wall flashing, and they applied it on a piece of L metal. Again, this is all facing due south, so it was like acting as a massive solar collector. And the ambient temperatures being 101, the substrate temperatures were read to be well over 200 degrees. And so, as everybody probably is thinking, yes, that membrane did melt, drip, and flow and create a pretty much a disastrous condition. So just be aware of these types of conditions, and certainly consider control joints would be the ideal thing. Concrete consolidation, the upper right-hand corner was a perfect example of poorly consolidated concrete. There was a cast-in-place concrete podium about several stories above grade for a parking garage for a very high-rise condominium in the city. And this is not what I would consider a continuous air barrier. So this was just something walking by and took a picture. Anticipate structural movement. The takeaway here is that pretty much most all air barrier manufacturers do have standard suite of expansion joints to maintain the plane of air tightness in continuity and to accommodate movements within the structure. Again, block is certainly prone to movement, but having lived in high-rise apartments for about 17 years, I can definitely attest to the power of wind forces, especially in the spring and the fall when we get the change of seasons. Again, thermal bridging, we talked about this early on. Any offset of the window condition relative to the primary thermal layer. We have thermal bridging. One workaround for this is many specifiers would take, again, either a layer of pink or blue insulation, or in some cases, closed cell spray foam, and apply it immediately below the window to frankly, continue the thermal continuity into the window units. So that would certainly be one workaround. Improper installation. One important key to note about air barriers, fluid applied air barriers, excuse me, is that fluid applied air barriers are, for all intents, self-terminating. So we always detail all of the rough openings and the penetrations first with a self-adhering peel and stick sheet first, and then we basically apply the fluid applied air barrier, again, depending on manufacturer, 1 to 2 inches onto the leading edge of the transition membrane. We don't need to fully cover the transition membrane with the liquid air barrier because this transition membrane is already providing air and water vapor tightness. We don't need to spend more of the owner's money than is really necessary. It is important also to point out that in some instances, not every project, every once in a while, this high density polyethylene carrier film is so dense that if we fully cover this with a liquid air barrier, that every once in a while we'll experience some alligatoring or cracking. And I've seen this on a number of projects where the project team shut the job down because they thought the air barrier was failing. Well, they didn't realize or didn't make the connection that we're already airtight and watertight. And again, manufacturers typically specify 1 to 2 inch overlap to basically seal the leading edge of these transition membranes. So just something to keep in mind. It's not the end of the world as long as we have that connection and we seal that leading edge. Self-adhering membranes, and again, I mentioned earlier, reverse laps are not the ideal because that's not how they're specified, but they're not the end of the world. We just simply hit it with the Butyl termination sealant. Self-adhering membranes do require the use of a laminate roller. So if we do see blistering, that might be indicative of the fact that the installer didn't use the roller on every square inch of the membrane. I saw in reading a number of manufacturers' literature, I encountered one manufacturer that suggests that hand pressure is sufficient for their self-adhering membranes, and I think that's a very dangerous proposition. The reason a roller is used is that it basically binds the adhesive-backed membrane to the primed substrate, and once that roller has hit the membrane, the membrane's just not going to be coming off. Hand pressure is just not enough to give it that serious pressure at that adhesive interface. We're getting a little bit close to running out of time here, but compatibility with peripheral systems. This is another good example. Masonry soft joints. A lot of air bearing manufacturers, present company included, we use SPS rubberized asphalt through wall flashings. And again, asphalt and polyurethane sealants, like we see in this example here, are not compatible with each other. And the result is that plasticizers from the asphalt bleed into the urethane or the silicone if it happens to be silicone. The result is sort of a non-hardening condition, generically referred to by some in the field as tobacco juicing. And that's obviously something we don't want to see. If it is possible for those soft joints to consider using an STPE or moisture cure type sealant in lieu of the polyurethane sealants, that would be a great workaround. So there's an option there. Materials based on substrate. I'm a big proponent for high build fluid applied air barriers over CMU, because CMU, as we saw in the early example, is a very porous, very rough surface. A higher build is going to also provide air sealings, same as a medium and low build around pre-existing masonry ties. However, if we have a structure that has pre-existing construction on either side, or say a parking lot, we may want to go with a self-adhering sheet air barrier. So both achieve the same objective, but self-adhering air barrier where pre-existing masonry ties exist provide another layer of detailing. So we're going to have to pre-seal around all those penetrations if we use a sheet type of system. So something to keep in mind. Pipe penetrations. This is another bone of my contention here is, with all due respect to the Air Barrier Association of America, who accept and allow for the use of a beta sealant around a pipe penetration, I think that that's a short-term type of solution. The reality is that a beta sealant is going to make contact with a 1/4 inch of the pipe, conceivably, and a 1/4 inch of the substrate. At some point over time, potentially that beta sealant might dry out and pull away, resulting in a whole unintended opening. Liquid flashing would be certainly a better approach, but in my opinion, the best practice would be what we see on the right, treating a pipe penetration the very same way we do a roof vent stack, for example. We do a finger flash, again, 3 inches of the fingers splaying out onto the deck, 3 inches onto the pipe penetration, and then we create a target apron, and then we apply the target apron over top of the fingers on the substrate, and then seal all 4 sides of that and seal around the base of the pipe penetration. In my opinion, that is a 100-year detail all day long. Plus also for the fact that transition membranes, again, they work tremendously in tension. So we really just a best quality detail there. Fastener penetrations I talked about early on, and I just don't think that there's we can't rely on this. If a fastener misses the framing membrane, the fastener is pulled out, no, the membrane will not magically fill back in. So just be aware of and be very wary of the term self-healing. Self-healing means just that. The hole will magically fill itself back in. The only thing it really does that is fresh coal tar pitch, and that's not what we use for air barriers. So just be aware of the limitations. D1970 is a great standard. Again, it raises the bar of performance, but it's not really the get out of jail free card that many might think it is. Wet dipping of fasteners. This is something that I rarely ever see, but it does add another layer of complexity, but I think it's a great practice and could certainly be included in specifications. Shelf angle detailing. Many manufacturers will promote the use of the termination bars. A lot of specifiers prefer them as well. This is a hedge against mortar droppings that might potentially dislodge the membrane. I've even heard a specifier say, I specify it because I don't trust the installers to get the self-adhering membrane installed correctly. Wall to foundation connections. In some instances, we see projects where there is no foundation damp proofing or waterproofing. So I always, again, promote the use of it at the minimum, a 6-inch transition membrane extending 3 inches onto the foundation and 3 inches on to connect the wall to the foundation. 2 beads of sealant on the outside corner of that track is just not enough for the long-term performance of that wall. The concrete might be irregular. Again, think about concrete, gypsum, and steel all coming together at that interface. They're going to have, again, markedly different coefficients of expansion and contraction. So we want to have a high tensile strength, high intention type of membrane connecting that portion of the envelope. And primer, again, for self-adhering membranes should generally extend. We want to see this visible 1 to 2 inches out beyond the edge of the membrane. An air barrier ABAA installer will certainly catch that. And flat panel joint treatments. All manufacturers typically allow for the use of a bead of termination sealant when the gaps on flat panel joints are at or less than 1/4 of an inch. We can certainly use liquid flashing. When the gaps are between 1/4 and 1/2, we again pre-fill those with termination sealant or liquid flashing, allow it to cure, and then we cover it with a 4-inch transition membrane. The detail on the right is not the ideal. We don't generally like to see that, but in some instances we do encounter that. If we have to apply any type of membrane, whether it's liquid flashing or self-adhered, the exposed gypsum core is very friable, so it's not going to gain a good foothold. So we generally have to hit that with some primer before the flashing is installed. And I'll finish up here with, again, my best practice for for flashing rough openings is to use a self-adhering aluminum flashing at a sill, wrapping it up 6 inches, and then the remaining jam and head conditions wrapped with a liquid flashing. I realize this is a 2-component type of system, but the reason I promote this is for the compatibility of the sealants that ultimately will be used to seal the window units to these types of conditions. There are really 3 options. Aluminum, we could wrap the self-adhering aluminum, which is backed by rubberized asphalt, on all 4 sides. We could use liquid flashing on all 4 sides, or we could just use the standard HDPE carrier film with the manufacturer's logo on all 4 sides. But there's sort of a good, better, best. I have a little write-up on that. I'm happy to send to anybody that's interested that discusses these 3 different approaches. But I will cut it here. But having air barrier inspections or audits are not a bad thing. They're a nominal cost add. And we're very fortunate, at least in our area here, to have really, really keen ABAA auditors that catches nothing, misses this guy's eyes. So it's always a good thing to have inspections. A little more money on the front end can help alleviate a lot of problems potentially on the back end. So with that, I'm going to close out because I'm out of time here. I ran 2 minutes long, but I just hope this was helpful. We just want to make sure that the drawings and specs are in sync with their delivered without ambiguity. And do consider how easy the air barrier can be installed during the design phase. Just understand that the majority of problems with air barriers are really at the penetrations. The biggest objective, again, is to stop bulk air leakage and subsequent water infiltration, and certainly consider a third-party audit. It's not a bad thing. But I really want to thank everybody for their time today. I know I probably spoke a little bit quick because there's a lot of stuff to cover here, but this is the quick 30-second WR Meadows commercial here. All of our air barrier products listed by spec number and title. I have some companion articles that I can send some organizers if anybody's interested. But with that, Isaac, I'm going to stop here. And if anybody has any questions beyond our Q&A here, feel free to email or call me. I'll turn it back to you, Isaac. Thanks.